Hi, good morning. First of all, a big thank you to Mosti for hosting this webinar to be broadcasted during the Minggu Sains Negara from the 1st to 7th of April. My name is Mr. Chia Chiu Yin. I am Head of IC Design here in MIMOS. And today I'll be presenting a webinar entitled Understanding Integrated Circuit IC Design and its Development in the Local Scene. So first of all, let me introduce myself. I am the Head of IC Design Lab here in MIMOS. I obtained my Bachelor of Science degree in Electrical Engineering in 1999, a long time back, from San Jose State University in the United States. After that, I obtained my Master's in Science, also in EE, in 2001, 2 years later, from University of California, Davis. And after that, after I graduated with my master's, I entered the workforce and I joined AMD in 2001. So while working, I did my MBA, which I obtained in 2006. So this was a part-time job. And of course, before I joined AMD, I did some summer internships at a few companies in the States. So while at AMD, I was a NOR flash memory designer. I was there for 8 years. So from 2001 to 2009. And AMD is Advanced Micro Devices. They merged, or they kind of spun out from AMD and became Spansion. And I think recently Cypress bought Spansion and Infineon bought Cypress. So now the NOR flash memory division is part of Infineon. So after I left Spansion, I joined MIMOS in 2009, and I've been here since for 12 years. My area of expertise is basically listed here: the analog IC design, sensor interface, motor controllers, NOR flash memory design services, and turnkey solutions. Okay. So today, this webinar will basically cover the following topics. What is IC design? Who designs the ICs and where are they made? The local E&E scene. How is an IC product made? Due diligence on the selection of a foundry, IC design flow, designing a CMOS inverter. And I'll end it with some of MIMOS IC design team capabilities and contribution. So I think this webinar is mainly tailored to the university students. So I hope you will enjoy some of the material I'm going to share today. Okay, so now MIMOS is basically, if you all don't know, MIMOS stands for Malaysian Institute of Microelectronic Systems. MIMOS is Malaysia's National Applied Research and Development Center. And as a strategic agency under MOSTI, MIMOS contributes to transforming Malaysia's industry through patentable technology platforms, products, and solutions. This photo is a little bit old, so the trees have grown pretty big right now if you come to visit us in Bukit Jalil. Okay, so now let me go directly into what is IC design. Now, semiconductors are everywhere, right? It can be found in your phones, your laptops, white goods, LED lights, electric cars. Almost everything we do throughout the day is powered by semiconductor integrated circuits. Now, the definition of IC design is the flow and process of integrating millions of transistors, resistors, and capacitors to achieve a specific function or application, resulting in an IC. Okay, so that's what basically the IC design is, to design a chip, which looks something like this. Okay, now to see how impactful IC design is, we just kind of look at some of the teardown of a Samsung Note 10 Plus. So if you look at it inside your phone, you can see that there's a lot of stuff inside there, which is basically semiconductor based or ICs. So if we take step by step and you open it up, you can see this is a board with the camera modules. If you look at it, there's a PCB together. There's a few PCBs actually stacked on top of each other. And if you look at it now, the boxes here are basically are the ICs or the integrated circuits that is part of the phone. Okay, as you can see, there are some from Samsung, some of the flash storage, some from Qualcomm, okay, and ON Semiconductors. So these are some of the companies that makes integrated circuits. So if you look at a different board, I think there were 3 boards. So this board basically shows that there are chips from Avago, Skychips, Qualcomm, Skyworks, Maxim. These are all integrated circuit companies. And again, this is the third PCB. PCB stands for printed circuit board. Now, if you look at it, there's a bunch of stuff also from, again, same manufacturers. You can see some of these are the RF front end circuits which allow you to communicate with the telco service providers. Okay, so you can see, I think I counted 21 ICs, and there are many more passives which are normally resistors and capacitors as part of your mobile phone. So actually, semiconductors is prevalent in almost everything that we use these days. Now, looking at this slide basically shows the number of semiconductor units that are produced since the 80s. So the growth of semiconductors has almost reached 1 trillion units only in 2019 alone. It's almost 1 trillion units from 32.6 billion in the 80s. Okay, so this growth basically started in the PC era in the mid 90s, and then we had the mobile phone era in the mid 2000s, and now we are in the era of Internet of Everything. Okay, now has anyone thought why the prices of our phones and laptops remain about the same, while the processing power gets better or more powerful every 2 years? So I guess the magic is actually from scaling of the transistor, as predicted by Gordon Moore. So the Moore's law basically states that the number of transistors in an IC doubles approximately every 2 years, based on he did a projection, or looking at the historical trend, he saw this. So people created the Moore's law to basically show the number of transistors. You can see here in the graph that it almost doubles every 2 years. Okay, so right now, if you look at 2019, the AMD EPYC Rome processor has almost 39.54 billion transistors. Okay, of course, it's a 9 die in a single package, but imagine the number of transistors that can be found on a single package. Okay, so now what is this transistor we keep talking about, right? So the transistor is one of the fundamental elements in the integrated circuit. It is called a semiconductor device, which can be used to amplify or switch electrical signals or electrical power. Okay, so let me show you what a transistor looks like. So now, transistor basically is a device. We draw the cross section of it looks like this. It has a source, and it has a drain and a gate. So normally a transistor is known to have 4 terminals, which you will see later on. But over here we are only showing 3: the source, the drain, and the gate. So and most transistors they call it a process node. So they label the node according to the length of the gate. Okay, the channel length we call it. Okay, L. Now if you can see that by measuring the channel length, we see that this is the process node or the roadmap of shrinking the transistor or scaling it. So back in the 1994, for example, we can see that the technology node back then was 350 nanometer. And every 2 years or so, it scales down by 0.7 or 1 over square root of 2. So now, by scaling down the transistor, you can see that okay, we can try scaling it down. Eventually, you will hit, you can make it too small. So what happens is the R&D folks have come up with FinFET transistors. Okay, so it looks like a fin. So what I showed you before that was planar transistors, where you can see that the drain and the source are here, and this is the gate with the channel length defined, where R&D folks started working on FinFET transistors in the 22 nanometer node. Okay, when the gate length was around 22 nanometer. Okay, so what happens when you shrink a transistor? Okay, what benefits do you get? So what happens is when you make the channel length smaller, you can pack basically more transistors in the same area. So now when you can pack more transistors into the same area, you basically get more functionality. Okay, so basically that's how it explains why your phones get more powerful. They got more features because you can pack more functionality within the same unit area. Okay, and of course, shrinking the transistor also helps reduce the delay. Okay, in IC design, we talk about logic gates and stuff. So ultimately, reducing the delay will enable the processor to run faster. Okay, because it takes a shorter time to accomplish each instruction or each execution. So this is what you see: your phone gets faster, or it remains fast. Okay. Now, when you reduce the transistor, also there's a lot of parasitic capacitance and resistance being reduced. Now, when you reduce capacitance, what happens is the switching time or the energy it takes to switch the transistor will reduce. So what you can see from that is, the battery life gets longer. Okay, so these are all the benefits from having scaling of the transistor. Now, as you can see, we are somewhere in the 2021, which is somewhere where the transistors right now, the channel length is close to 5 nanometers. Okay, so very small. That's how they can pack so much transistors into a unit area. Okay, so now let me continue into the next slide. So who designs the ICs and where they are made? So this slide basically shows the top 20 companies in terms of semiconductor IC sales in 2019. And you can see Intel is #1 with Samsung #2. Some of these MNCs have design operations here in Malaysia, like Intel and Broadcom. They are both based in Penang. There's also the Infineon from Germany, which has a design center and manufacturing facility in Penang and Malacca, respectively. These MNCs are the ones that design the chips, okay, that go into your electronic devices, your PCs, your laptops. Some of these MNCs here don't manufacture their chips. Okay, so these are companies called fabless design companies, like Qualcomm, like Broadcom. They do design the chips, but they don't manufacture them. So now the people that design and manufacture these companies are big. They are like Intel and Samsung and Infineon, where they call IDMs, integrated device manufacturers. Okay. Now for the fabless companies or the MNCs, for example, Apple doesn't. They design their own chips, but they don't manufacture them. So where do they make their chips? Now they make their chips in foundries. Okay, so these are some of the top 10 foundries in the world. So basically, TSMC is #1, Taiwan Semiconductor Manufacturing Center Taiwan Semiconductor Manufacturing Company. It's located in Taiwan. Samsung is located in Korea. UMC is in Taiwan, and Global Foundries is in the United States. SMIC is located in China. So you get all these manufacturing companies or fabs or foundries that manufacture ICs for the fabless companies. Okay, we have companies like Infineon, onsemi, Fuji Electric, X-Fab, SILTERRA, Mimos. These are all companies in Malaysia that have fabs. Mimos has its own wafer fabrication facility. It's called SILTERRA. Recently, it was sold to Dagang Exchange in February. Okay, and of course, Mimos also has its own fab right here in Technology Park, Bukit Jalil, Kuala Lumpur. We have a 200mm R&D fab. We can run CMOS processors in the 0.35 and 0.5 and 0.35 technology node. And we also have specialty process for high voltage and for MEMS devices. Okay. Now let me talk a little bit about the local E&E scene before we go into what IC design is all about. So this slide basically shows the semiconductor economic. This basically shows the contribution of the E&E sector to the Malaysian economy. So in 2019, the E&E sector contributed the largest percentage, which is a 38% export from the country, and valued at 375 billion. So E&E products, not just IC design, but overall everything that relates to E&E is a big export product from Malaysia. And these are some of the 10 E&E multinationals. So I mean, in Malaysia, there are two big groups, where the multinationals and the local companies. So the 10 E&E multinational companies in Malaysia, I think most of you know: Western Digital, Panasonic, Intel, Samsung, Flextronics, HP, Dyson, First Solar, Infineon, Osram. So some of them are in Penang. Dyson is in Johor. First Solar is in Kulim. Infineon is both north and south, and Osram is in Penang. And there's if we go to the 6 E&E large local companies in Malaysia, we have Karsam, Unisem, SILTERRA, Inari Technology, Dominant Opto, and Globetronics. Okay, so now where do these companies play, right? I mean, there has to be a value chain. So now if we go to the next slide, this slide shows basically the E&E semiconductor ecosystem value chain. So in every product, I mean, in any industry, there's always a value chain. So this is I obtained this slide from the Edge Markets. Basically, try to segmentize the E&E semiconductor ecosystem. So basically, if you look at it, starting from left to right, the high end or high value add end of the semiconductor chain is integrated or IC design. Okay, so these are some of the companies which play in this segment, but I will show you there are more, not just these two. There's of course the wafer fabrication, which is where, you know, normally you start off with the design. You get specifications from customers and you design it. So now once you're done designing, you send off your design to be manufactured in a wafer fabrication facility or foundry. And in Malaysia, there is SILTERRA. These are Malaysian companies. And then what happens is once the die has been manufactured, it will be packaged and tested. Okay, so now these are some of the companies which do packaging and testing. And this is also where Malaysian companies kind of add value. Okay, so the high performance test software, socket and stiffener, and ATE and equipment manufacturers come in. So ATE is automated test equipment. Okay, they come in, and these are the companies which support this segment. Okay, now once they're done testing and package, basically it goes to the EMS, which basically assembles, manufactures, and does production. Okay, and these are some of the companies which support this segment. And these companies basically support companies like Huawei, Samsung, and Apple that makes the final end product. And they need somebody to manufacture for them. So these are the companies, EMS, that does the manufacturing. I think some of the famous ones are like Flextronics, okay, which is globally known to make Apple products. Okay, so they are the ones that eventually obtain the final product. Okay, so this is the value chain. And as you can see, IC design is right at the front and the highest value. So as you can see, multinationals like Intel, AMD make the chips. And we also have local players that are in this area. Now, looking at the next slide. Okay, so these are the 17 SMEs working in the IC design segment. And most of them are based in Penang or KL. So we have Simit, Key ASIC, MyMS, Innovatech or Ascend Microsystems, Opstar, Infinix, Skychip, Matic. We have Emerald Systems, ICE, Cryptic, Iris Labs, Logic House for ASIC, My Nano Designs, and Elpcore. Now, to help the IC design community, MIMOS is a member of MIGDA, which was formed to basically help build Malaysia's reputation as a strong IC design hub, and also to champion and create a vibrant, profitable IC design industry. MIMOS also formed the IC Design Consortium to kind of encourage more local IC design organizations to join and take advantage of the economies of scale to basically build new business ventures. Okay, so this is MIMOS trying to help some of the local IC design companies. to grow. Now, I think to grow the ecosystem, I mean, there are also other organizations. MIDA and MITI are very involved, and of course EEPN, Electrical and Electronics Productivity Nexus, is set up a web page to promote basically Malaysia's E&E companies to the world. This is the website, www.eemm.com.my. Now, this website basically showcases all the it's like a one-stop portal for people to search for services and E&E SMEs in Malaysia. Okay, so if you visit it, you can see all the companies and their relevant services. Okay. Now, the next few slides basically will talk about how an IC product is made. Okay, so basically initially the webinar was mainly on, you know, who makes it, where do you make it. Now let's look at the steps or the flow on the IC itself. You know, what do an IC design company does, okay, to make the product. So I kind of try to define it into, I split it up into 3 stages. So stage 1 is normally always looking at the customer or the market coming to you with a specific requirement or specifications. So with that, you know, say I need to design a IC that can do this. You know, it must cost this much. This is the volume. You know, it must have, you know, for example, an LED driver, right? So there is an LED that they want to drive, and they want to on your light bulb. So there's a chip, a semiconductor IC inside. So there will be specifications of how much wattage the light is. So all of this gets put into some kind of document, which they will bring to the IC design company. Now, the people inside the company will basically, who are IC designers or architects, they will basically look at the proposal or the specifications, come up with technical feasibility studies, and look at the cost structure to see whether they can do the job, number one, and also whether they can make money out of it with sales and whatnot. So if, let's say, doing their due diligence, they believe they can do it, they will basically start designing. Okay, so in the design phase, basically there is a few flows, designing an analog chip, an ASIC chip, or an SoC chip. So that's the design phase. Now for stage 2, after you finish designing it, normally they fabricate the design, or you manufacture it, or you make it, you know, into a real IC. Okay, once you make it into an IC or a die, you have to package it, and you do the first silicon testing. Okay, so first silicon testing, again, there are 3 outcomes from the first test, right? So normally if it works, you pass it to the customer, right? You can sample it, they call it sample. So you provide it to the customer, they sample it, you know, they test it in their board, or they test it in the light, they're able to power up the light, and you can get the right wattage and current and stuff like that. So then it's good, right? What there's the chip, some of the chips that come out sometimes, it works 50% or it partially works. Ultimately, it's an engineering sample. We don't call it a final IC. So since it's an engineering sample, you can pass it to the customer and tell them that based on an errata that there are some bugs to it that will be fixed going forward in the next revision. Now, of course, the worst is when the chip doesn't work at all. So if the chip doesn't work at all, ultimately you need to basically fix the bugs, retape out, and go through the whole design phase again, and retest. And then hopefully the second revision works, and then you can pass to the customer. Okay. So ultimately, this is the normal flow on stage 2. And if the customer likes the device and it works and they don't have any issues with it, then basically they want to see more units. So they will go to stage 3, which is the running production lots, which basically means you get more chips or you get more ICs. And to do that, basically, it is multiple wafers. Okay, so you run multiple lots or multiple wafers in a lot. And normally it's 12 wafers per lot. And ultimately, you have a lot more die. So each die basically will rest on the wafer. Okay, each of your designs will basically be patterned on the wafer, which I will show you later on. So now, once you have a lot of chips, what you can do is you can you run what you call functional and reliability testing on those chips, because you're gonna make a lot. There's bound to be failures, so they need to be tested and run through reliability testing. Okay, temperature testing, thermal shocks, ESD zapping. They just make sure that the chip is solid. It works when it's out in the market. Okay, and eventually you would have a burn-in before the product is sold. Okay, so this is basically the 3 stages of how do you make an IC product. Now, designing an IC is not really rocket science. I mean, going through an engineering degree in EE and focusing on IC design, definitely you understand it. But let me just go through some of the steps taken to as in part 2, basically, which is the feasibility and technical feasibility and cost structure analysis on which foundry to select, right? The due diligence on the selection of a foundry. Okay, so so why SILTERRA? So right, we selected SILTERRA for this example. So let's look at the due diligence. So SILTERRA basically was founded in 1995 and based in Kulim, which is in Kedah. It is a 200mm wafer foundry offering a CMOS fabrication process for ICs. They have advanced logic, mixed signal and radio, RF and high voltage applications. Okay, so from a logistic point of view, you can see that it is very close to the airport. It's very close to tests and packaging houses in Penang. So from a logistic standpoint, it is a good place to basically to use SILTERRA as a place to make your ICs if you were to ship the die to Penang for packaging and testing. Okay, now if we look the technical specs of what SILTERRA, the process or the technology portfolio, you can see that SILTERRA has technology, has in mass production. Mass production means they are basically people are making tons of chips using their wafers, so their process is very stable. So if you can see, they have the mainstream process, which is the logic, mixed signal, RF, high voltage, and memory or OTP, one-time programmable memory. So if you can see, the 100 nanometer down to the 110 nanometer. And these are some of the flavors which they have, different voltages for the core, which is the logic, and the I/O. So basically, the design that we want to work on will be utilizing the C18G CMOS logic process with core voltage or logic voltage at 1.8 volts and I/O voltage at 3.3. Okay, now once we select the process, for example, C18G, we need to review and see whether the process meets our requirements, right? We want to design something, we got to make sure that it has the right features. So we got to make sure, oh, it can go up to 6 metals. There is the 1.8 volt core and the 3.3 volt I/O voltage. It has SRAM, this is the size, and it has, for example, MIM capacitors. So these are some of the things that we need to look at, the process features, to make sure that it meets our requirements. So talking to a fab, they will list down a lot of their rules. Okay, so there's the physical design rules, there's the electrical design rules, and also support. The SILTERRA, basically fabs provide support for you to design your chips. So for example, if using this process, we have the standard cells and the I/Os that are provided to help you design your IC. Okay. Now, another factor to consider or to review is basically the cost of fabrication and the schedule. So what you see right now here is to save costs, we have this thing called a multi-project wafer schedule or multi-project wafer, which runs and enables multiple customers to participate while sharing mass costs. Okay, so what that means is basically if you have one mask, and it is subdivided into different sizes, you can put design 1 is company 1, design 2 is a different company. So you can put all of your designs in one mask, and basically this is how it gets repeated on the wafer. So you as customer 1 will share the cost with the rest of the customers using this wafer. Of course, you don't get the whole, you don't get so many dies because of this, but the cost is very much reduced, okay, depending on the number of people that share the cost of manufacturing, okay. Another thing to note is also the schedule. The schedule is very important. So I think SILTERRA has this on their website, which shows you the dates of when you need to get your design ready. So when a customer comes to you as a design house and say, I need the IC in 12 months, you know, tested and verified. So working backwards, you know, before you can test the packaged chip, you need to make sure that it takes 3 months to fabricate the chip. It takes 1 month to package the chip. So you're left with, you know, and maybe 2 months to test the chip. So you got 2, 1, and 3. So basically you have 6 months to basically do, they call it the back end flow, where you have left with 6 months to design your IC. Okay, so having a schedule is very important so that you can plan your deliverables to the customer. Okay, so now saying that, let's dive deeper. So basically we've seen the flow on how do you get an IC product, and of course we looked at some of the questions to evaluate a fab, okay, before you even do the IC design. But now, okay, we've selected the fab in SILTERRA, and we're going to look at 180 nanometer. But how do you design the chip? So what I'll show next is basically steps for custom analog IC design flow. Okay, so the steps we take, or the design company takes to design a chip, basically using the analog flow. Okay, again, so like what I said just now, for example, if the chip you need to design is the LED driver, so definitely there are specifications for it. So based on those specifications, you start designing. Right? You put your these are basically transistors on the left here. This green thing is a transistor, and you have the blue lines are basically connections of the transistor. So basically, you put they call it a schematic together, which is a bunch of transistors hooked up with input and output pins. Okay, that does a special function. Okay, so it's called schematic entry. Now, once you put your schematics together to create that function, you have to run simulations. Okay, simulations are basically stimulus you pump into your design to verify that it works according to your specifications. So basically, the design phase happens here, where you enter your design, you simulate, and you keep making sure that your results are correct. Okay, so this is where it gets iterative. Okay, where you come up with, this is the high value add work that is going into IC design. Why IC design is not as straightforward. Okay, because this is where the design phase happens. Put in your design and simulate. Okay, look at the results and make sure that it meets the specifications. Now, if we are comfortable with the simulations, and we know that the results are good, we take the design and we basically lay it out. Okay, we call it a layout. So basically, this picture here, what you see is a representation of the schematic. Okay, so what happens is we have to make a physical representation of the schematic. Okay, of the transistor. So we hook it up, we make a physical representation of the transistor, and we call it layout. Okay, we draw it out. And after drawing it out, we can see later we have to verify that the layout is correct. So we run a few checks, which I will go through later when we go through the design of a simple inverter. Okay, some of the checks we run. After running the checks, we do a parasitic extraction process, and basically, and we do this post layout sim. So after the layout verification, it looks correct, extract the parasitics, we have to basically rerun the simulations. Now, if the simulations meet, that there are only two outcomes. If the simulations meet the specifications before, see, you have one simulation step here, you have some results. Does the post layout simulations match or are close to the pre-simulation, pre-layout simulations? If they are, then basically you are done with your design. If they are off, then you would have to go back and fix the layout or modify the layout so that you can reduce the parasitic capacitance and resistance and, you know, stuff like that, and go through this whole flow here. So basically there are two big loops which needs to be done, and normally they run in series, right? You do this first, then you do this, all right? So you're like a waterfall thing. So you gotta get your schematic design done before you do the layout. Okay, now so the next slide is basically where I give an example of how do you design a CMOS inverter, right? CMOS is complementary metal oxide semiconductor. So if you look at this, we start off again with specifications, right? So these are just some of the specifications I've put together to kind of explain the design of an inverter. So we have the supply voltage, 1.8 volts. Normally supply voltage, we give some kind of tolerance, plus minus 10%. So we get like plus 10 would be 1.98 volts and minus 10 would be 1.62. Driving a load of 4 inverters. So you have one inverter driving 4 inverters. This inverter needs to work at 3 different temperatures, minus 40 degrees C, 25 C, and 125 C. And what is the design specifications which you need to meet, right? So for example, in this case, we want to optimize for the delay of the inverter, right? It has to be less than 1 nanosecond. Okay, so now to do design, ultimately we need EDA tools. These are the 3 big EDA tool vendors. They basic Cadence, Pantographics, and Synopsys. So they basically produce software to allow you to do your design. Okay, it helps with the design flow, and from schematic entry all the way to simulation to back-end and layout. Now, this is SILTERRA's design flow. Again, similar to what I just shared. Basically shows you the schematic capture, the pre-layout sims, the layout, the verification, the post-layout, and the tape-out. So tape-out is like the final step before you send your design to the fabrication of the foundry. Okay, so all foundries usually come up with a flow they use to qualify their process. So for SILTERRA, these are some of the flow that they use to qualify their process. So for the first step, for example, I'll just talk about the first step. So for schematic capture, what you see is they use the Cadence as the EDA tool vendor, and they use the schematic. Okay, and the inputs schematic is the EDA software. It's actually virtuoso, but it's a schematic editor. So the inputs to that is libraries, cells, and views. Okay, so this is where you do your schematic capture, where you put your transistors inside and hook them up for a function. And and for the simulation pre-layout, before you lay out, what is needed from the fab is SPICE model and a netlist. Okay, so when you take the model and the netlist and your design, ultimately you use, if you're using Cadence, you run your simulations using Spectra. And for Synopsys, you use HSpice. So basically, these are the tools which will be used to simulate your design. Okay, and so on and so forth. So you have different tool vendors for different functions. The layout and verification, you have this. Post layout verification, you have Mental Caliber, Synopsys, Hercules, and Cadence, Asura. And basically for parasitic extraction, You have Mentor Caliber XRC, Synopsys Star RCXT, Cadence Azura RCX, Fire and Ice QXC. Okay, so so let's go back to the basics. I think let me cover what a MOS transistor is. Again, it's one of the key elements, one of the elements in IC design, which is the transistor. Okay, so again, this is non-exhaustive. So there are two main types of transistors. They're called the PMOS and the NMOS. So normally transistors have 4 terminals, which is the bulk. But in this diagram, it's not shown. If you cut the PMOS and NMOS across, we get the cross section. So for the NMOS, what you see is N. So normally the N stands for the doping. They call it the N plus doping. So so N basically is made from group 3 in the periodic table, which is normally either boron or gallium. Okay, so and P is basically the PMOS device is made out of the source and drain are basically P type elements, which is from group 5, which is either phosphorus or arsenic. Okay, so basically an NMOS and a PMOS are made from group 3 devices, which is the NMOS, and group 5 devices, which are the PMOS. Okay, now as you can see, I mentioned there's the 4th terminal, which was not shown in the previous symbol. So you have the drain, gate, source, and the bulk, okay, or the body. Okay, same with an NMOS. It's a 4-terminal device. So you have the drain, gate, bulk, drain, gate, source, and the bulk. Okay, so this is the cross section of an NMOS and PMOS. And again, to represent, this is the symbol of a transistor, and there are only 2 parameters actually IC designers get to choose for sizing a MOS transistor, which is the width and the length. Okay, so you can only change 2 parameters. Okay, of course you can stack them, you can put them in parallel, you can put them in series. You can connect different configurations between the gate and drain, gate and source. But in terms of dimensions of the transistor, what you can do is you can only change two dimensions: the width and the length. Okay, the length is what I discussed earlier, which is the channel length of the transistor. So and the W is the width of the transistor. Okay. So the rest of the functions of a transistor, for example, the thickness, the oxide thickness, the threshold voltage are all fixed by the foundry. So looking at the EDR is very important to know what kind of threshold voltages exist in the transistor and whatnot. Now, to design an inverter, if you can see here, okay, an inverter basically is made up of two transistors, right? You have a PMOS. The symbol of a PMOS is there's a bubble, and the symbol of an NMOS, there's no bubble. Okay, so in this diagram, we have this what do you call a truth table, and normally what that means is you have an input A, you have an output Y. So when you pump in a 0, so in IC design, that we represent 0 as in 0 volts, and we can sometimes represent 1 as binary 1, binary 0, but 1 sometimes can be represented as a VDD, which is the power supply. Okay, so in this case, a 0 or a ground basically means that the NMOS is switched off and the PMOS is switched on. So what does it mean by switch on? Basically, when you switch on, basically it looks like a switch. A transistor is basically like a switch. So you control the switch by putting a voltage on the gate. So in this case, we put a 0 on the gate of a PMOS. And when you put a 0 on the gate of a PMOS, it turns on. Okay, so when it turns on, basically it creates a short from VDD to Y. So that's why the output becomes a 1. Okay, so most of these are quite fundamental if you have done some VLSI or if you've taken some of these courses in the university. But if you haven't, or if you learned some of this maybe in year 5 or form 5, then this is a NOT gate, okay, a tak gate in Malay. So this is an inverter. So it inverts the signal. Whatever you see at the input gets inverted and when it goes to the output. Okay, and the same thing vice versa. You put a 1 at the input, you get a 0 at the output. Okay. Now, like I said earlier, you have only 2 dimensions, or in this case, you have 2 transistors, so you have 4 dimensions or 4 parameters which you can change, which is the width and the length of the PMOS, the width and length of the NMOS. So these are some graphs you can get from literature, which shows you how to maximize the noise margin of an inverter. How do you size it? And of course, this graph basically shows you the propagation delay versus the sizing ratio, which is beta here, which is the ratio of the width of the PMOS divided by the width of the NMOS. Okay, so looking at this graph, we want to minimize the propagation delay through the inverter. That's the design specifications. We potentially want to size the width a beta of 2, where the width of the PMOS is twice that of the NMOS. Okay, so that's how we will eventually size this inverter on the PMOS side. We'll choose the width of the PMOS to be 2 micron. The width of the NMOS is 1 micron. So the beta is basically 2. Now, for channel length, since when we say 180 nanometer, normally we refer to the length of the channel of the transistor. And normally, if we say 180 nanometer, that's the minimum or the smallest channel length the transistor can be designed with. So we've kept it minimum in this case. And what we do is after that, we run simulations. So we pump in stimulus, we pump in an input, and we'll get an output. So this is basically an example of an input waveform, and this is an example of an output waveform. So, and here we represent it with voltages. Okay, in this case, if the input voltage is a 0, the output is at VDD or 1 volt, and vice versa. If the input is at 1 volt, the output will fall to 0 volts, as you can see here. Okay, and of course, normally, as you can see previously, the specs mentioned that the inverter needs to run not just at 1.8 volts on the power supply, but there is a tolerance of 10 plus minus 10%. So when we run our simulations, we can't run with just 1.8 volts on the power supply. We have to run all 3 here, variations or permutations or combinations. Same with temperature. So the temperature that we need our inverter to work is at minus 40, 25, and 125 C. So looking at permutations, you got 3 and you got 3 here. Now, I put this, if this was an interactive talk, I would ask you why we have 5 times 3 times 3 number of runs to run the inverter. So ultimately, 3 of this is the VCC variation. This is the temperature variation. So this 5 basically is, they call it the process variation. That is, that is modeled in the models from the lab of the transistor. So normally we have a PMOS and we have an NMOS. So what that means is there are basically typical corners. There's the weak corner and the strong corner. So basically you have the TT, the SS, which is the strong corner, the slow and the weak, or what do you call you got a fast corner, you got a slow corner, FF and SS. Okay, so in total combination, there are 5 process corners. Of course, there are more, but for an introduction, normally there are 5 corners we run to model the different variants or the different variations in the transistor. So, but if you multiply them, you would get 45, and that would be the number of runs you run to get your waveforms to measure the delay of the inverter. Okay, so this few slides basically shows that if you are done with your simulations and your design is good, this is just the layers of how a transistor eventually gets built. So these are just the layout, what a layout, you draw a layer, and this is what it looks like in silicon. So this is for the N well, and you basically have N diffusion, P diffusion, poly, contact. Okay, so eventually, if you look at it, this picture here looks pretty much like a cross section of the NMOS and the PMOS, and the representation which a layout engineer sees looks something like this. Okay, metal layers are something which are given by the foundry and as a layer. So if you need to route connections between drain, gate, and source, you can use metal layers. To run your lines, you can draw something, basically a metal one, and basically have contacts to show that it has connection made. Okay, and this is basically the final layout of an inverter. You can see basically this is the physical, it's a physical representation of the inverter. So the pink one is where the poly is. You have the PMOS at the top, and you have the NMOS in green at the bottom. So anytime you see a poly crossing a diffusion, you get 1 transistor. And if you see a poly crossing a diffusion, which is the N implant, you get 1 transistor. So this is basically where your NMOS situates, where the drain is here and the source is here. Okay, and if you look at it here, this is where a PMOS sits, because the poly crosses the P diffusion. Okay, so this is where the drain is, and this is where the source is. Oh, sorry, this is where the drain is, and this is where the source is. Okay, basically they're interchangeable, the source and drain. Now, after your layout is done, there are a lot of checks that still need to be done to make sure that the design is right. So one of the checks which foundry wants you to do is called a DRC. Okay, so a DRC stands for design rule check. Basically, there are a bunch of patterns which they need you to check, or the tool basically will check it for you based on the rule set given by the fab. Okay, these are some of the specific rules which, when you draw your transistors, need to meet in terms of spacing, the width, and enclosure. Okay, so this is where the EDA tools come in. They help you automate some of the checking. It reads in a rule deck from the fab, checks your design, and gives you errors if it doesn't meet the checks. And basically, you need to have a feedback there and fix the design to make sure that it passes all the DRCs. Okay. Now, the next check that usually they go through is the LVS, which is the layout versus schematic. So here, what we do is we have the layout on the left side, and we have the schematic on the right side. So we need to somehow match it up. So we again use EDA tool to go and run the LVS. Now, to match up both these two, right? Because if they don't match, then it's going to be a problem. You can't, whatever you have simulated here will not be able to be simulated here. Okay, so that's called an LVS mismatch. So, but if it does matches, normally we call it a match, and basically the schematic design, that whatever you have done here matches what you have done in the physical representation of a layout. Okay. The last step, well, not really the last step, but this is one of the final steps, which is the extraction I mentioned before of the wire resistance and wire capacitance. So these are some of the, again, wires are basically modeled again with width and length. So you control the width and the length to get the resistance of the metal. For example, this is a metal, and you have a width and length. And capacitance, basically assuming your metal runs in the middle of something on the top and at the bottom, you can see that there are parasitics capacitance from your metal line running. Looking into if you look at this picture, looking into the diagram, you can see that it is there are parasitics to the top and bottom because it looks like a parallel plate capacitor. So this, again, another EDA tool comes in where it extracts this parasitics, and eventually what you do is they call it a back annotation. It puts it back into your schematic, the resistance and the capacitance, and basically you rerun your simulation to make sure that the delay and whatnot is still within specifications. Okay, so I think that is basically it for the designing an inverter. So that's what IC design is all about. So basically going through a specification all the way to getting it right and running it and making sure it meets the specification. So that is the whole IC design flow or value add, the high value add activity. Now let me change gears and basically look at MIMOS. Okay, so what is MIMOS IC design team? What is our capabilities, and also some of the contributions that we have done. So if you look at the next few slides, we are able, the design team, we have a team here, and it is able to do design consultancy. We do consultancy on some of the IP developed by us. We do full turnkey solutions, which is going from specifications all the way to GDS2, which is the final file you send to the foundry for tape out. And we also do IP development. We design domain-specific IPs. And finally, we also do system-level solution development, which is how the IC interfaces with the rest of the components in the system. Okay. This is roughly the IC design team in MIMOS. We have the AMS team, we have the FPGA ASIC team. So AMS team is mainly the analog team. They design analog circuits. We have the FPGA and the ASIC team, which designs digital circuits. And we have the layout, right, which is the custom. There are two groups in here, which is the custom layout. You draw transistors by hand, you route things by hand. And there is the place and route, where you use, again, another EDA tool to kind of place all your transistors or your gates, and basically it will route it based on a specific constraint. Okay, so we have two teams here that basically can do both custom layout and place and route. We also have a team that does CAD automation, and PDK is process design kit. Basically, we do some automation of some of this process design kit from foundries, and we have a group that does IC testing. Okay, now these are some of the IPs that we have worked on. These are mainly analog IPs. We have a bunch of digital IPs also, but I forgot to list them here. Some of these IPs are designed in some of the fabs, international fabs and local fabs, SILTERRA X Fab, UMC, Global Foundries, TSMC. We do have a few products from ICs that we have worked on, which I will share later. And we also do some services to help some of the local SMEs in terms of, for example, IC packaging, testing, and system prototyping. Okay, so what you see here is one of the product that the IC design team in MIMOS worked on. Is called the Green Motion Controller. It's a permanent magnet synchronous motor controller, and permanent magnet synchronous motors are known to be highly efficient. So what we did is we designed a controller chip, which can basically control the motor. We have done some prototyping it on a washing machine. So we've put a PMSM motor at the bottom of the washing machine and retrofit it to make the gear ratio, to change the gear ratio. And ultimately, if you look at this, we managed to turn the washing machine spin it basically, wash and spin. Okay. This is another IC we worked on, the team worked on, which is an encryption IC. Basically, it's a general purpose security chip, and basically it has a list of comprehensive cryptographic algorithms like AES 128.256, SHA-256.384, some of this ECDH P384, okay, and ECC 256 and 384. So this is the chip that we put it inside to a socket, and basically these are some of the interfaces that we test the chip with. Okay, so yeah. This final product that I will highlight today would be the variables, a three-phase sensorless variable speed drive AC induction motor controller. So what we have here is we have an FPGA board which we code the flow of a flowchart of a AC induction sensorless motor controller to, okay, so so ultimately we have done a POC, a proof of concept, on 3 kilowatt amp motor. So if you can see here in this video, basically it's the setup of our system. So ultimately, for safety reasons, we are running it off a DC power supply, 580 volts. That's the DC link, basically going into the inverter. Yeah. So the high voltage board and the FPGA is all there, and ultimately the three-phase output goes into a blower. Okay, so the blower we mount it onto a setup on the rig, and ultimately with the variable speed drive, you're able to control the speed of the AC induction motor, right? Because most AC induction motors only operate at one speed. So to be able to operate at a different speed, you need to have a controller to basically change the speed of the motion controller of the motor. Okay, and last but not least, we have done some of these services for some of these SMEs in Malaysia. So recently we worked with Opstar on some of these back-end services like IC packaging, testing, and demo board development by utilizing some of the E&E value chain in Malaysia, where we did packaging in ASC. We've done some of our testing, IC testing in TestUp, and PCB generation with Jack Engineering. Okay, and what happened was a company was formed, Iris Labs, that took the chip that basically is an AI chip, which is a implementation of a KNN classification algorithm, and they are trying to make a product out of it, which they call it Iris Sense. It's an all-in-one facial recognition, attendance logging, and contactless temperature measurement. So you can check out their website. They're basically trying to come up with a homemade Malaysian product, okay, based on a Malaysian IC, all done basically in Malaysia. Okay, some of the other contributions with the design team does is also we work with universities on education talks, internships, and IC design projects. So I just highlight a few here that some of the talks we've done at UTHM, UITM, First City, UM. And of course, we've taken some of the interns in from some of our local U's and to basically work on some of our projects in MIMOS. Okay, and of course, we also do participate in international and local conferences. And we sometimes get invited to do final year evaluators and also act as industrial advisory panels on some of these universities. Okay, and finally, when there is a request from SMEs, we do provide training to the local SMEs. Okay, so to summarize the whole talk, some of the key takeaways from the webinar is basically IC design is a high value add activity. It takes a team to design an IC. As you can see, you need a team, and you need the EDA tools. So you need a combination of people that know how to use the tools and know IC design, use the tools, get a specification, and make the IC. Okay, so it's not a one-man show. You can't get things done alone. And whatever I shared today is but a tip on the iceberg for IC design. So what you have seen is just designing an inverter, but that things get more complex. And I think what happens is, to be a good IC designer, ultimately for university students, you need to master the fundamentals, which is usually what you guys study in the first 3 years before you do your elective. So what IC design is all about is always based on the fundamentals that you have learned in the first 3 years, which ultimately, if you want to specialize, you need a master's. Okay, so this is just my input as an IC designer for the past 20 years. Okay, the fundamentals are very important to become a good IC designer. Okay, I think that's about it for today. Thank you for taking the time to listen to the webinar, and hope that this piques your interest in becoming an IC designer in the future. Okay, thank you. Okay, bye.